Okay, so moving to the next, unsymmetric addition. Heading unsymmetric addition. Now the three symmetric additions are over. Okay, the next is unsymmetric addition. Unsymmetric addition. Okay, in your textbook, the unsymmetric addition is defined on the basis of Markovnikov rule. Markovnikov rule. This is actually a carbocation mechanism. Okay, so Markovnikov addition, observe if there is no rearrangement. What? This is actually a carbocation mechanism. So we can observe, you know what is Markovnikov rule? Okay, fine. Listen. So anyway, the unsymmetric. Okay. Right. So I think you are familiar with the unsymmetric alkene. Unsymmetric alkene. Unsymmetric alkene means groups across double bonds are entirely different. Okay. If I have but 2E, what it is? But 2E, what it is? It is a symmetric alkene. Symmetric alkene. Unsymmetric alkene means, for example, unsymmetric alkene is but 1E. But 1E is an unsymmetric alkene because the groups around bonds are entirely different. Okay. So most of unsymmetric alkene have difference in hydrogen of double bond. The double bond have one hydrogen here. Here it is 2. Here the double bond have 1 each. This is symmetric. Okay. So in most of unsymmetric alkene, there is a chance for a difference in hydrogen across a unsaturation. Okay. Then the Markovnikov rule is negative part goes to with the least number of Markovnikov. I think you know that. If I have an unsymmetric alkene like RCH double bond CH2, okay, which on treatment with the reagent HA, where H plus and A minus, the negative part of reagent is A minus. Then according to Markovnikov rule, A minus goes to carbon where number of hydrogen is lesser, and H plus goes to here. Okay, and you obtain R CH CH2. Here is the A. Here is the. This will be the major product based on Markovnikov rule. I think you are familiar with that. Okay, but this follows only if there is no rearrangement. Okay, so you should know the reaction on the basis of mechanism. Okay, so this is a secondary idea. Ready? This is not well applicable for your objective questions. Okay, this is a secondary idea, treated as a secondary one. Okay, the primary concept for the unsymmetric addition is its mechanism. So listen here carefully. Okay, that's a carbocation mechanism where rearrangement is possible. Okay, so the mechanism of unsymmetric addition is electrophilic addition. Mechanism is electrophilic addition. Electrophilic addition means first of all electrophile is added, followed by nucleophile. That's why electrophilic addition, where the addition of electrophile is the slowest step or rate determining step. That's why it is initialized as electrophilic addition. Listen, I have an alkene RCH double bond CH2. Okay, if I am adding HA to that alkene, first of all H plus may induce to the alkene, and this is the rate determining step. So this bond may polarize. Okay, usually the bond polarized to the terminal end, minus plus. Okay, so your H plus CH2 minus. What happens? R CH plus CH3. Is that okay? So by the addition of, what is H plus? Electrophile. By the addition of electrophile to the alkene, you obtain a carbocation. Ready? So this is a intermediate. This is a carbocation intermediate. Where in this reaction, what possible? What possible? Rearrangement possible. Okay? Ready? Is there any rearrangement in this one? No. Because you don't know anything about R. If you know something about R, then there may be rearrangement. If there is no rearrangement, so it is clear that in this structure there is no rearrangement. Agreed? Then what about the next? The attack of A minus. Okay, so A minus attack to this portion, right? What do you obtain? RCH A CH. Okay, is these two are same? Yes or no? Yes. Why means there is no rearrangement. If there is any rearrangement, then this positive charge will be here, right? Okay, so A minus will be in this R. So it doesn't follow Marconi curve rule. Okay, so Marconi curve rule is a second. You simply consider whether there is a rearrangement or not. If there is no rearrangement, you can make it on the basis of Marconi curve. If there is a rearrangement, then it should be on the basis of mechanism. Is it okay? Markovnikov know that. He know that this electrophilic addition, okay, where the A minus goes to the C plus, right? If there is no rearrangement, then the C plus generated will be middle on the most stable C plus will be generated on say non-terminal portion, right? If the carbocation is generated on terminal portion, what happens? It becomes primary. If it is on the non-terminal portion, its degree may increase. So he know that the most stable carbocation may generate in non-terminal portion. Okay, where the A minus can attack. So we generalize that A minus goes to carbon with a lesser number of hydrogen. Okay, if there is no rearrangement. Okay, that idea is generalized by Markovnikov. Okay, for your exam, for your questions, you have to consider it is actually on the basis of simply this is the idea. Once you have a look on that molecule, you can imagine that whether it's a rearrangement or not. If there is no rearrangement, you simply add with the, or you can proceed on the basis of Markovnikov. Else, it should be in the mechanism wise. Okay, so this is a primary one, and you treat this as a secondary. Okay, so first, listen. If I have a molecule like this, ready, which is added with the HBr. Okay, what do you have to think? You simply polarize the bond to the terminal end. Always you polarize the bond to the end. So this to the end become minus plus, where H plus to the minus. Agreed. What happens? Okay. Then is there any rearrangement? Is there any rearrangement? Yes. So it may rearrange like this to form. Then Br minus attacked to form a compound like this. This is a major product. Okay, what about the Markovnikov addition? Simple Markovnikov. Which is the Markovnikov portion? This one. Right? Here only one hydrogen. Here we have two. Here we have two hydrogen. Here only one hydrogen. So the if somebody know only Markovnikov rule, his answer is this one. Okay, but the real answer is this one. Okay, so Markovnikov rule only applied if there is no, and you know how to, I think you know how to identify whether it is rearrangement or not. Okay, fine. So this is a primary important concept. Then you can show Markovnikov. So the rate of this reaction depends on what? Degree of carbocation formed. Okay, because that is RDS.
എപ്പോഴൊന്നും വി ഡയറക്ട്ലി പ്രൊപ്പോർഷണൽ ടു ടി എന്ന് പറയാൻ പറ്റില്ല, പ്രഷർ കോൺസ്റ്റൻ്റ് ആയാലേ പറയാൻ പറ്റുള്ളൂ. എപ്പോഴും പി ഡയറക്ട്ലി പ്രൊപ്പോർഷണൽ ടു ടി എന്ന് പറയാൻ പറ്റില്ല, വോളിയം കോൺസ്റ്റൻ്റ് ആയാലേ പറയാൻ പറ്റുള്ളൂ. അതുതന്നെ അതേപോലെ തന്നെ എപ്പോഴും പി ഡയറക്ട്ലി ഇൻവേഴ്സ്ലി പ്രൊപ്പോർഷണൽ ടു വി എന്ന് പറയാൻ പറ്റില്ല, ടെമ്പറേച്ചർ കോൺസ്റ്റൻ്റ് ആയാലേ പറയാൻ പറ്റുള്ളൂ. അപ്പോൾ കോൺസ്റ്റൻ്റ് ആയിട്ട് നിൽക്കുന്ന ആളുടെ കണ്ടീഷൻ അനുസരിച്ച് മാറും, അത്രേ ഉള്ളൂ. Can show Markovnikov rule also, okay, and write that point. Markovnikov rule is only applied if there is no rearrangement. Okay, keep that point. I'll give you some examples that based on rearrangement, then based on Markovnikov. Okay. Ready?
always polarize the bond to the terminal position and simply consider the hydrogen, the minus charge occupies by hydrogen, and you obtain a carbocation. Okay, check whether rearrangement possible or not. If possible, do it. Finally, the negative part. So entirely unexpected products are obtained due to rearrangement. Expectation means Markovnikov rule. Okay, so a normal person have an expectation of Markovnikov rule, but entirely different product may obtain. Okay. H2O in H plus means H plus and oh, it's minus. So here the and Br minus. This bond jumps to here. Ready to form a carbocation like this. And from here we have an hydrogen to shift. Carbocation like this. Finally the attack of Br minus to form the product like this. Is it okay? Everyone? The next. Here it is H plus and OH minus. So this bond polarized towards the end. Okay. The polarization may be to this carbon also. If to this carbon, this become minus and H plus attack on this and become a primary, it rearranged to become secondary. Okay, if the positive charge is here, it shifted to become secondary. So no need of showing that step. So usually the better carbocation you obtain terminal end. Okay, that's why generalized as you simply polarize to the terminal. Okay. Fine. H plus attack to form a carbocation like this, where this methyl may shift, right? Finally the attack of is to form the product like this. Okay. Question may be like this: acidic hydrolysis of 3,3-dimethyl butadiene. 3,3-dimethyl butadiene predominantly forms, and the choice also in based on names. 3,3-dimethyl like that. Okay, but unfortunately it is 2,3. It become 2,3-dimethyl. 2,3-dimethyl butane 2. It's due to methyl shift. Okay. What about here? Here it is H plus and Cl minus. So H plus to the end to form the carbocation like this. Okay. And chance for shifting. We know rearrangement, it is very easy. So the Cl minus is in the ring, but where the bond is in outside of ring, reagent is inside of ring through rearrangement. Here also this is H plus and Br minus. To form a carbocation like this, since this is a most stable benzylic position, right? This is a benzylic position, agreed. So there is a shift. This is simply a secondary, but this is a benzylic position. Benzyl carbocations are more stable. Okay, so there is a rearrangement chance, so that will be here. Finally, the attack of Br minus to form a molecule like this, which is named as 1, 2, 3, 1 bromo, 1 phenyl. Okay. Fine. Now, examples with the without rearrangement, which means simple Markovnikov. And that is just for introducing some kind of reagents. Okay. For introducing some extra reagents. That's all. That's all about the aim of showing molecule with without a rearrangement. Okay, to introduce some reagents like HOCl, NOCl, like that. You have to know which one is plus and which one is minus from a reagent. Then only you can add like that. Okay. What about this one? Is this follows a Markovnikov rule? Or is there any rearrangement? What about the carbocation formed here? Okay, so there is no need of rearrangement. So this is the attacking position. Agreed. Where that is also given by Markovnikov. Okay, so the Markovnikov position and carbocation positions are same. Y means no rearrangement. So you simply based on Markovnikov rule. So you should write major product here, minor product here. For example, if the first one is addition of Hi, second one is addition of HBr, third one is H2O in H plus, fourth one is dilute sulfuric acid, fifth one is concentrated sulfuric acid, sixth one is HOCl, next one is Br2 in H2O, next is NOCl. Okay, so you know the Markovnikov position. This is the Markovnikov position. So negative part on this position, the product will be major. So you simply know the reagent H plus and I minus. What about the first? I minus to the Markovnikov position, where hydrogen in this position, right? Okay. And about the minor? Minor. Here is the hydrogen. Here is the hydrogen. Okay. So for this examples, you simply want to know what about the electrophile and nucleophile. Ready? So that I will explain, and you can show the product. Okay. H plus and Br minus, H plus and OH minus. Listen. Wait. This much is okay. What about dilute H2SO4? Dilute means the content of water is which is in presence of an acid. So which is something like water in acid. Dilute H2SO4 means H2O in H plus. So the very same product obtained, H plus and OH minus. But if it is concentrated sulfuric acid, it will be H plus plus HSO4 minus. HSO4? What about the polarization? HSO4 minus. Listen, HSO4 minus where the negative charge is actually in oxygen. So this have to write OSO3H. There is a difference. Listen. What do you mean by RSO? But here it is. Here the negative part is not SO3H, OSO3H. That is entirely different. Here it is ROSO3H. This is hydrogen sulfate. You know, H plus and HSO4 minus is hydrogen sulfate, bisulfite or hydrogen sulfate. So here the name is alkyl hydrogen sulfate, not sulfonic acid. This is not sulfonic acid. Okay, that is hydrogen sulfate. Both are different. There is a small change. So here the polarization will be H plus and O SO3H where the negative charge is in O. Okay, what about HOCl? HOCl is hypochlorous acid, OH minus and Cl plus. OH minus and Cl plus. Listen, bromine in H2O means, listen, bromine in H2O means the main component is HOBr. HO, just like HO, just like HOCl. So this indicate HOBr. So OH minus and Br plus. The last one is nitrosyl chloride. Nitrosyl chloride, where NO is the plus and Cl is the, there is a difference. This is OH minus Cl plus, but this is NO plus Cl minus. Okay, should know which one is the electrophile and nucleophile, then only you can design the product. Okay, now you know everything, so show the products. Consider this as an extra information. Both are different. Okay, no need of ready. Fine. Extra hydrogen in bond line. any atom other than hydrogen you have to show. You have to show the OH lines. Anything other than hydrogen will be there. Okay, if NOCl is added, you should indicate, you should show NO and Cl also. How much carbon is there? The second one. Second one. How many carbons? Where is the So this example simply indicates that you have to know the polarization of reagent. Then only you can add in a Marconi core or anti-Marconi core or in any sense. Okay. So just to introduce some reagent. That's all. First of all, you have to check whether the given alkene were rearrangement possible or not. Ready. That's the criteria. Okay. What about the answer? Here is your bromine. Here will be no need to show hydrogen in bond line. Okay. Okay. You should show 4 carbons. Ready? This only 3. Carbon is to here. Okay. Don't forget it. Butane 2 volt, butane 1 volt. Very same. Okay. Next, butyl hydrogen, butyl 2 hydrogen sulfate, hydrogen sulfate. That's hydrogen sulfate. Next, HOCl, OH is the negative part. Here you should show the chlorine. Okay, ready? Okay. The next two I will write here. If it is HOVR, like this. The last one NOCl, for the negative part is Cl. So Cl will be on the Marconi position. Nitrosyl chloride, the molecule is known as nitrosyl chloride or Tilden's reagent. NOCl is named as Tilden's reagent. NOCl, nitrosyl chloride. Okay, fine. Ready. In some cases, we observe anti-Marconico addition. Anti-Marconico addition, where the negative part goes to carbon containing lesser number of hydrogen. But there is no rearrangement because the mechanism is entirely different. Okay, so there you simply place the negative part on the carbon with a lesser number of hydrogen. Okay, there are three possibilities for anti-Markovnikov addition. The first one is in presence of peroxide. Second one is in the case of hydroboration oxidation. It is in your alcohol, hydroboration oxidation, preparation of alcohol from alkene. And the last one is the presence of electron withdrawing group. So the next, anti-Markovnikov addition. Anti-Markovnikov addition. Anti-Markovnikov addition. Anti-Markovnikov addition. There are three cases where anti-Markovnikov addition is observed. Okay, anti-Markovnikov addition means you know the concept. Negative part goes to carbon with a greater number of hydrogen. Exactly the reverse of Markovnikov. And the first one, peroxide effect or Karash effect. First one, peroxide effect or Karash effect. Peroxide effect or Karash effect. Okay. And this is only in the case of HBr in peroxide. Well, only in HBr in peroxide. Peroxide means any compound having OO linkage. It is only observed with HBr. Moreover, the HBr should be in peroxide. Okay, that is, we have an alkene RCH double bond CH2 which on treatment with the HBr and the reaction is in presence of a peroxide. Okay, where R may be anything, it may be hydrogen also. If it is hydrogen peroxide, HOOH. Okay, R may be anything, there should be a peroxide linkage, that is a condition. So what happens means the major product will be hydrogen here and bromine here. This is the major product, just reverse of Markovnikov. Okay, reason is where in the previous case the mechanism is electrophilic addition, right? Electrophilic addition. First of all the electrophile H plus, and then the rearrangement, then the nucleophile. But here in presence of peroxide the mechanism is free radical mechanism. Radical mechanism means radical addition observed here. Listen, let me show the mechanism and it is given in your textbook. So initially the peroxide undergoes homolysis to form side, what it is, alkoxide or anything, alkoxide free radical or free radical. R may be anything, okay, it may be hydroxide free radical, to form free radical. Peroxide itself undergoes homolysis to form free radical, and in presence of that free radical our HBr undergoes homolysis. In presence of that formed free radical homolysis, where H is abstracted by the free radical to form free bromine free radical. Okay, well, first peroxide undergoes homolysis to form the free radical, and in presence of the formed free radical your HBr undergoes homolysis to form the bromine free radical, the free bromine free radicals. Okay, now the reaction is under the control of bromine free radical, and you have an alkene on treatment with the bromine free radical. Agreed? So what are the chances? In presence of bromine free radical, this bond also cleaved homolytically. So there are two chances. Either the bromine free radical to here, chance number 1, or the bromine free radical to here, chance number 2. And this is the RDS. Okay. So what are the chances? Or what about the products? R, CH, CH2. If the chance is 1, what happens? What happens? Bromine to here, it becomes CH2. We have to form a secondary carbon free radical. Okay. Or what about the 2? If it is 2, what happens? If 1 or 2? If it is 2, what happens? The forms bromine to here, right? To generate primary carbon free radical. Since this is the rate determining step, you can say that this will be the major. This is the most stable, right? Secondary carbon free radical is most stable. So this will be in a major quantity, yes or no? Since this is the most stable free radical formed, this intermediate will be major, most stable. So the production of this stable intermediate will be more feasible. Okay, so in this system, this free radical will be in a higher quantity. Finally, the attack of what? Finally, the attack of H dot. There is no role for H dot because H dot can attack in a free radical position. That's the only idea of H dot. Okay, so which product will be in a major quantity? The first one, right? Yes or no? Yes, and it seems to be a anti-Marconico addition. Okay, why this observed means because the mechanism is entirely different. Okay, where the intermediate formed is carbon free radical, where this carbon free radical will be the stable one. So this will be the major quantity. So the corresponding product will be major. So there is two possibility where the major is this one. Okay. So you simply know why it is so. It is due to the changing mechanism. Okay. For this mechanism, your HBr should be your HBr have to cleave homolysis, right? HBr should undergoes homolysis. For that, there should be a free radical. That's why the reaction is only in presence of peroxide. Okay. The purpose of peroxide and the mechanism. Keep it in mind. Okay, why this is only in HBr means, in case of your HF and HCl, the bond energy is relatively high. So HF and HCl not undergoes homolysis like this. Okay, so this reaction is not observed in HF and HCl. Then why it is not in HI means, HI have ready homolysis. Okay, because the bond energy is comparatively lower than HBr. But the formed iodine free radical is unstable. It can't exist as alone. It readily combined with another iodine free radical to form I2. Okay, so due to this reason, the reaction is only observed in presence of HBr, come peroxide. Okay, so write that also. Why not in HCl, HF? So only in HBr in peroxide, okay? So the second case where Markovnikov rule is anti-Markovnikov addition observed is HBO method, hydroboration oxidation method. Okay, hydroboration oxidation method. Ready? And that's not a peroxide mechanism. HI have ready homolysis, but the formed iodine free radical unstable combined to form I2. Your formed free radical should exist as a free radical. Then only the reaction proceeds. Okay. These two not form free radical, but I didn't form free radical, but it can't exist as alone for a long time. Okay. So the second is hydroboration oxidation method, HBO method. This is actually not peroxide mechanism. This is an entirely different mechanism, and it may be discussed in your alcohols. Okay. Now I am showing the logic for designing the product. Okay. You are given an alkene, which on hydroboration. How can you identify the reaction is hydroboration? Means by identify the reagent. The reagent is diborane in the first step, followed by alkaline H2O2. Treatment with the alkaline H2O2. Okay, this reaction is given in your textbook, alcohols. So that there we can observe the addition of alcohol. This is hydration actually. Hydroboration oxidation is actually a hydration, where the reagent simply H plus and OH minus, where H goes to carbon with a greater number of hydrogen and OH goes to carbon with a lesser number of hydrogen. Okay, this is not peroxide mechanism. The mechanism is described in your alcohols, so it may be discussed there. Show this. So third case where anti-Markovnikov addition of observed is in presence of electron withdrawing group, you know, minus I group, presence of a minus I group, and that is not in your textbook. Okay, listen, wait, listen here. Here is a electron withdrawing group just nearer to an unsymmetric alkene. Okay, and if you a reagent, let it be an HA. What is actually happen means this electron withdrawing group withdraws electron density towards itself. So this carbon become a positively charged one. Okay, once this become a positively charged one, this carbon try to absorb electron from the next one. Okay, so that there is no chance for the polarization towards the end. If the polarization, because this carbon, since this carbon is a positive, this carbon try to absorb the electron density towards itself. Okay, so there is no chance for the polarization towards right. So there should be the polarization towards to the middle. Okay, ready? So what happens? This become minus. If the bond is polarized to here, this become minus and this become, and this plus is due to the inductive effect. Okay, and this minus plus is due to polarization. So your H should, this is H plus and A minus, right? Agreed. So H plus will be here and A minus will be here. So it seems to be an anti-Marconi addition. Agreed. So the R, CH, still now the electron withdrawing group is there, but the addition seems to be a anti-Marconi compound. Okay? Fine. Try to understand the reason. Ready? Why the bond polarization towards the middle carbon? So this ketone is a minus I group. So in presence of this keto group, bromine goes to the terminal end like a anti-Marconi addition. Okay. Ready? Okay, so this bond cleaved, hydrogen here, bromine here. Okay, and that is due to minus I effect. So that's all about unsymmetric addition. So additions are over. There are some oxidations. And that's all about alkene, oxidation. Oxidation and by means of and you know your Miller ozonolysis. Okay, and the ozonolysis may observed in any. So here is the first in your alkene, and it may be in your alkyne and in your benzene. Okay, so that's a common reaction. So now the rest is oxidation. Okay, so there are two oxidation. That's about alkene. And one more reaction, that is polymerization. And you know the polymerization. Okay, polymers is over. Ready. So no need of showing polymerization of polythene like that. Okay, it is discussed in a detailed way. So we have only oxidations in your alkene. Once alkene is over, alkyne will be easy. Exactly similar to alkene. Alkyne is exactly similar to alkene. So it will be okay. Fine. So we are moving to the oxidation. Put it as a heading, oxidation. Acidic KMnO4 may oxidize, will be discussed in the oxidation. Acidic KMnO4 brings the reaction in different manner. That will be discussed, okay, in your ozone or oxidation. Oxidation, there are actually two types. One is ozonolysis and then there is strong oxidation. Okay, so you simply show first strong oxidation. So strong oxidation. Strong oxidation. Strong oxidation. Strong oxidation. Strong oxidation means the oxidizing agents are either hot acidified KMnO4, hot acidified KMnO4, hot alkaline KMnO4, hot, it's not cold, hot, cold is base reagent, that is hydroxylation, you know. So will be like this, or hot acidified K2Cr2O7. Okay, so these all are simply considered as strong oxidizing agents, okay, which can cleave CC double bond, CC double bond. But it is very easy. Listen, there are 3 chances for designing the product. If you know that, then the reaction is very easy. There are 3 chances for unsaturation. Every unsaturation will exist in a 3 possibility. Any one of the 3 possibility. That is, if there is a terminal unsaturation, then that double bonded carbon may have 2 hydrogen. Ready? Then that terminal unsaturation with this powerful oxidizing agent become HCOH. HCOH. But HCOH is relatively weak. Weak means it's not acidity, its strength is poor. Acidity is much higher for formic acid than your benzoic acid or acetic acid, like that, okay? And we'll be discussing carboxylic acid. Okay, and this is simply the strength, whether it is strong or weak towards an oxidizing agent, means formic acid is much weak towards an oxidizing agent. So this is a powerful oxidizing agent. The system consists of powerful oxidizing agent. Once formic acid formed, it becomes CO2 and H2O. It again oxidizes to form CO2 and H2O. So the first idea is okay. If there is any terminal double bond, the product will be CO2 and H2O. So the first chance is your double bond may be with 2 hydrogen if and only if it is in a terminal position. The second chance is the double bond may have 1 hydrogen if it is in a center position. Ready? And it on oxidation, you simply make it as COH. Okay? And the third chance is that the double bond may be without hydrogen. Okay, these are the 3 different chances. I'll give you example, then it will be okay, fine. Which on oxidation, you simply make it as ketone. Listen, listen here. CH3, CH, double bond, CH2. What it is? Propene. Your propene with a hot acidified KMnO4. Ready? So listen, you simply cleave these bonds and make the products. Cleave the bond. What about CO2 plus? That's okay? That is okay? What about, so this is over. What about the rest? That is a middle double bond. Ready? Means double bond without hydrogen. Sorry, without branch. This is a double bond with the branch. That's why the hydrogen is not present. Okay. So this is double bond without branch. Make this as COH. Make this as. So the remaining will be the CH3 COH. Is it okay? Ready? So double bond with 1 hydrogen, where that group become COH. Whatever be the remaining valency, that will be the. Okay, fine. Listen, if I have another example, CH3C, CH3 double bond, CH, CH3. Okay. Which reaction with the acidified K2Cr2O7. You cleave the bond. What about this one? Acetic acid, because double bond with the hydrogen. Ready? You simply place 2 oxygen here. That's the idea. And here only 1 oxygen. It becomes ketone. Okay. So there are 3 possibilities. Either the double bond with the 2 hydrogen, then it should be a terminal double bond. Okay, or a double bond without hydrogen, then it should be a non-terminal without branch, or a double bond without hydrogen, then it should be a non-terminal with the branch. This is the only possibility. If you know how to design the product, then it is over. There is no other, no need of showing more and more examples. These all are the possibility. Okay, fine. What about here? Here, CH3, CO, CH3. Okay, ready? So in this reaction, this much idea is enough for designing all product. Okay, so keep this and show 2 examples how to apply it in a question. Okay, to know how to apply it is in a question. Ready? Enough. So first of all, you should copy the reagent, powerful oxidizing agents. Okay, so it is clear that if a hydrogen, then there will be addition of 2 oxygen. If there is no hydrogen, addition of 1 oxygen. Okay, there may a chance for asking the reverse idea, reverse. Question may be like this also. So you have to think in a reverse pattern. So it is clear that if there is a hydrogen, then there will be an addition of 2 oxygen. If there is no hydrogen, addition of 1 oxygen. So write a question like this also. Reverse pattern. Ready. Acetic acid. What about the structure of acetic acid? COOH. What about butanol? Butanol. A ketone with a 4 carbon. A ketone means there should be a CO in the middle of the position, right? Both have alkyl group. So only butane 2,1 is possible, right? So CH3, CH2, CO. Okay. What do you have to do? You simply pick the oxygen. Okay. And then make a bond there. Remove the oxygen and make a double bond. Is it okay? Ready? Because the alkene there is no oxygen, right? So you are asked to find the alkene. So there is no oxygen. You simply remove the oxygen, make a bond. Okay. So what about the category? CH3, CH from acetic acid. Okay. Then the double bond. Then there is a C. Double bond which is attached to this C. Agreed. Followed by CH3 and CH2, CH3. Is that okay? Okay. So just reverse thinking. Because maybe like that also. Enough. That's all about that oxidation. We are moving to the next ozonolysis. Ozonolysis. So oxidation number 2 actually. Okay. Ozonolysis. This is okay. Fine. If there is if the product is CO2 and H2, then you simply there will be a terminal bond. Okay. So if you know the clear picture about the reaction, you can think in a reverse or any pattern. Okay. So ozonolysis is also very easy. You have to know some conditions. If you know that, then it is very easy. Okay, so I'll explain the condition to design the product. Okay. Ozonolysis are actually two types. In your textbook, only one type, that is reductive ozonolysis. But for your examinations, it may be oxidative also. Okay. So first of all, you realize that there are two types of ozonolysis. The first one is reductive ozonolysis, and the second one is oxidative ozonolysis. Then what is the difference means? In reductive ozonolysis, in the first step, the ozone is added in presence of CCl4, or simply ozone will be there. In the oxidative ozonolysis also, the first step is addition of ozone. Okay, but in the reductive ozonolysis, the second step is the form. Once you added ozone, the forms ozonide, and the ozonide on treatment with the zinc in H2O, it is said to be reductive. Or if it is with an acetone, DMS, dimethyl sulfide, two methyls which is attached to sulfur, that is said to be dimethyl sulfide. Usually that is DMS. It's a non-polar solvent, that's all. Non-polar aprotic solvent. So either in ZnH2O or in DMS, the mechanism will be reductive. Okay. What about the second step in oxidation? Is H2O or it is H2O. So this is the difference between these two. Okay. So here, double bond with the hydrogen become CHO. In reductive ozonolysis, double bond with the hydrogen become, it's not CHO. Okay. Double bond without hydrogen becomes CO. Just like your oxidation using KMnO4. But here it is only CHO. Whereas in the case of oxidative analysis, double bond without COOH. Okay, and double bond will become CO. Okay, there is a difference. Ready? So the difference is, the first difference is here. Ready? In the identification of reagent. And the second difference is here. The rest are same. Okay. DMS is dimethyl sulfide. 2-methyl group which is attached in a sulfur. So let's have some examples. CH3, CH double bond, CH2.
to do yourself.
bonds, right? This is cleaved. CH3, CHO plus CH2O. CH2O is CH2O. CH2O means formaldehyde. H, CHO. Okay. Second one is CH3COH plus HCOH. Third one were 2 molecule of CH3CHO. Here it is 2 molecule of CH3. So one point is clear that if you are given with a symmetric alkene, you obtain only one kind of product. The number is 2, but the nature of product is only acetaldehyde. If it is an unsymmetric alkene, you obtain mixture. If the unsim alkene mixture, sim alkene, same kind. Okay. What about the next? What about this position? What about this position? It's a double bonded carbon with or without hydrogen? Without hydrogen. This is a double bonded carbon with so without hydrogen become ketone like this. Here clear OO. Ready. With hydrogen become aldehyde like this. Okay. So acetone and acetaldehyde. Ready. If more than one unsaturation, cleaved OO, cleaved OO. So CH3, CHO plus CHO, CHO is already written, glyoxal. It is written in your polymers. Glyoxal, oxalic acid, glycolic acid in the case of polyglycolic acid in your polymer. So CHO is glyoxal. The last one is HCHO. Okay. What about this corner positions? If the unsaturation is ring, then one product may form. Only one product with the 2 carbonyl combo, 2 carbonyl group. Here we have one hydrogen, right? This is a double bond with the hydrogen. This is also with the hydrogen. So cleave to form O. The molecule will be a dicarbonyl compound. Okay. 1, 2, 3, 4. Succinaldehyde. Okay, butane 1,4-diol. Butane 1,4-diol. What about here? This is without and this is with the, so whatever it may be, cleave to give bonds. So this become aldehyde, right? Like this, and this become a ketone. Okay. Ready? Actually, that forms an ozonoid intermediate. Okay. That forms a ozonoid intermediate. So maybe they are asked to find or asked to design the ozonoid. It's very easy. You are given with an unsaturation. Agreed. Okay. Which one treatment with the ozone? So this entire unsaturation cleaved to form a new ozonoid. And this is how ozonoid can be designed. Listen, you simply leave the whole bond, okay, and make a O connection like this and a single connection like this. Ready? Using 3-oxy, then you obtain ozonoid. Which one treatment with the this oxygen moves with the zinc, and here it cleaved to form the bond. Okay, so no need of showing that one. They may be asked to find, you know how to design the product. Okay, no need of designing through the ozone intermediate, but you may ask to draw, or you may ask to identify the ozonide. Okay, so it is in the ozonide. Okay, this is said to be alkene ozonide. If I have an example like this, what about the ozonide? This bond cleaved, right? Okay, the ozonide will be something like this. Okay, ready? So you should know how to design the ozonide. That is the only idea. This one. This one. Diozonide may form. Okay. Ready? Leave the bonds. Bring the ozonide. Okay. Leave the double bond and make a connection like this. Ready? So show this and write 1 or 2 examples. This is okay. You leave the bond and make your ozonide connection. That's the only idea. Ready? Okay. Reverse may also ask here. It's very easy. Simply leave the oxygen and connect by a bond. Okay. CH3, CH2, CH, which is connected to the C. Where C have a methyl. Moreover, okay. So A on ozonolysis forms 2-oxo-hexanal. So hexanal means what? Aldehyde of Aldehyde of 6 carbon. How much carbon now? 5. 6. Aldehyde means a terminal position have a double bond. Double bond. This aldehyde 1, 2, 3, 4, 5, 6. Ready? Okay. So this is the carbon number 1. Carbon number 2, 3, 4, 5, 6. This is 5 oxo. I'm sorry. 5 oxo. 5 oxo hexanal. So this is a molecule. Okay. Ozonolysis gives only one product, means that one product with the 2 keto group means ozonolysis of a molecule or the product having 2 carbonyl with one combination means it will be a cyclic. Okay, we already show the examples, right? So think this is in a cyclic pattern, or write this is in a cyclic form. How it is? How much carbon? 1, 2, 3, 4, 5. Where 5 have a oxo and 1 have a oxo. This one there is a methyl. Is it okay? 3. Then a ring of how much carbon? A ring of how much carbon? 1, 2, 3, 4, 5. A ring of 5 carbon where there is a bond. Okay, if this is a 5th carbon, there will be a methyl group. Ready?